Hello, everyone, and thank you for joining us in another exciting series in optics. The series involves concave and convex mirrors. So we'll start this video by introducing terminology for these two mirrors. Then we'll analyze the image of an object sitting outside the focal point of a concave mirror and one inside by using ray tracing and thin lens equation. And I kept the thin lens equation because we did the lens already, and it's the same equation that we use for the lens we will use for the mirror. And then we'll work out some exercises just to illustrate the point and maybe do a lab. So before we begin, thanks again for joining us. Please like, subscribe, comment, and let us know what you think about this. So let's begin. So this is a concave mirror. Concave mirror is like a bowl. The reflective side, this is the reflective side. This is the dark side. Yeah, it's just like an aluminum bowl that you have maybe in your kitchen. Okay. This is the focal length. This is the focal point right here. So that's the focal length. And everything is measured from this line right here. This is the radius. Again, it's in a shape of a part of a sphere. So it's got a radius to it. Okay. There's the optical axis. There's the vertex or the center. Okay. Here, no light exists, dark side. Here, light happens only on this side. Okay. And this is about it. I mean, objects will definitely sit here. And their image for a concave mirror could be either on this side or on this side. We'll see that later. Okay. And the same terminology is used. This is distance to the object. That's the height of the object. If this is the image on this side, this is the distance to the image. And that's the height of the image. And here, also the distance to the image, height image. This is a convex mirror. Convex mirror is like a Christmas ornament, the shiny side of it, or maybe the right side mirror on your car, the door mirror. Those are convex mirrors. Okay. The focal length and the radius are on the dark side of the mirror. Obviously, no object sits here because light comes in from here. Okay. So the object sits here. There's the distance to the object. The image, we'll see that for this type of mirror, will always be here. Right? And it will be virtual. And there's the eye. There's the height of the image. There's the height of the object. Okay. So again, there's the dark side. There's the light side, or the reflective side. Okay. So the lens equation and magnification, again, we still use the same equation as we used before. 1 over f is 1 over di plus 1 over do. And these mean the same thing. Distance to image, distance to object, and then focal length. And the magnification has negative di over do, or h sub I, h sub o. Okay. So same thing as we've been doing before, except right now we've got a mirror. So light does not go through the mirror. Okay. Light reflects off the mirror. For a lens, light goes through. An image could form on the other side of the lens, real image. But for a mirror, there is no real image on the other side of the lens. Light does not go through a mirror. So let's talk a little bit about sign convention, similar to what we did for lenses. So here I have both mirrors right here. So the focal length, f, and the radius, r, which is 2f. So the radius, we said this is again, these shapes are made from parts of a sphere. Again, think of a Christmas ornament. And if it breaks, if you take part of that broken ornament, you could think of it as a convex mirror. But to begin with, it was a sphere, so it had a radius. And here's the radius. Here's the focal length. The radius is twice the focal length. Sometimes you're given the radius, and then to work the problem, and then the focal length is just half of that. Okay. Now the focal length for a concave mirror is positive, and the radius is positive. They are on the light side of the reflective side. Reflective side of the lens, they're positive. For a convex mirror, here's the focal length, a focal point. So here's the focal length, and here is the radius. They are negative. They're on the dark side of the mirror. Okay. The distance to the object is positive when the object is in the reflective or the light side of the mirror. So as long as the object is here, here, or here, doesn't matter, here, all these distances are positive. If the object happens to fall here or there, this is for a concave, convex, then it's going to be negative. And usually this happens, we're going to work out something like this, where I probably would say, okay, here's an object, put a lens over here, and the lens is going to cast, obviously, the light's going to go through this lens from this object, and it's going to cast an image that may sit on this side, maybe like this. But now, the light doesn't get to this image. There's that mirror that interrupts it. So this now will act as an object to the mirror, but it acts as a virtual object. And we'll see how we do this. Okay? So otherwise, in just a single mirror equation or a single mirror problem, all objects are positive. All distance to the object is positive. Now, distance to the image is positive when the image is on the reflective side. That's over here. Again, this is different than lenses. Lenses, because light goes through it, a real image is formed over on this side, and that gave us a positive DI. But here, if DO, right here, let's put it like this. This is DO. And if DI is here, it's positive. But if DI is here, image here, here's DO, and here's DI. This one and this one, they both have negative DI because they are on the dark side of the mirror. Okay? Here, DI is negative. Here, DI is negative. Here, DI is positive. Right here. Because it's on the light side. Right there. Okay? So basically, anything on the light side, focal length, radius, object, distance, image distance, is positive. Anything on the dark side is negative. Okay? Again, same as before. If the object is pointing up, HO is positive. If object is pointing down, maybe here, it's negative. And again, but for our convention, we always take our HO pointing up if we have just one single mirror. But if you have a compound system like a lens and a mirror, the object may be pointing down, as I illustrated maybe here, right there. If I put a lens over here, this object is going to go through the lens, produces an image over here pointing down, but this image now acts as an object to this mirror. So here we have an object that's not only virtual, but also pointing down. So that in this case, H sub O for the mirror is negative. Okay. And H sub I is positive, again, if the image is upright. So if I have an image like this, HI is negative. But if the image is upright, usually those are virtual images, HI here is positive. Here is negative. And here, if I have an object right here, the image is going to be over here somewhere. So HI is going to be negative. This is the I right here. Okay. The magnification, again, is positive if the image is upright, and negative if it's inverted. And that's basically it. Similar to lenses, there's a little bit of differences in terms of, like right here, we will never form an image over here. I mean, a real image over here. The real image will be formed over here where the light is. Okay, it only has one focal length. There's no two focal lengths. You could have a mirror like this with the focal length and the radius are on the dark side, here on the light side. And again, everything else just about the same. So this is sort of like your guide when we start solving problems. And in the next video, again, we're going to look at the image properties for an object outside the focal point of a concave mirror. Again, we're going to use ray tracing, which is slightly different than the lens, and then use the thin lens equation. So again, thanks for your time. I hope you found this very interesting. Let us know in the comments, and hope to see you in the next video on concave mirrors. Bye.